Alright, ladies and gentlemen, welcome back to another exciting day of mathematics. Alright, 2.6 day 2, rational functions. We're going to be graphing these things by hand still, but they're going to have slant asymptotes, so as the name implies, asymptotes that run diagonally, and possibly holes in the graph. Let's get started. Okay, so slant asymptotes. If a rational function's numerator's degree is 1 higher than the denominator, well, then there's going to be a slant asymptote. And that's going to play out as I'll show here in the division. So we're going to have to divide the denominator into the numerator and go from there. Okay, now synthetic division may be possible sometimes, but it's not in this case because we have a coefficient. Alright, so basically we'll have to set up our long division. I know, just deal with it. Alright, we got 2x squared plus 3x minus 5. The good news is we're only doing this because the degree here is 1 higher than here. Okay, that's the only time we're going to have to do this, so it's definitely not going to happen all the time, but it is something we have to be aware of. Alright, so over here again we're trying to match the 2x to the 2x squared, so all we need to do that as an x, multiplying, we get a 2x squared plus x, and again with this, probably a better idea to change all the signs and then add instead of trying to think of subtracting. So as we do this, those cancel, and we're left with a 2x, we bring down the minus 5, and then again lather, rinse, repeat. Okay, we got to match a 2x to a 2x, so all we need there is a 1. Multiplying, we get a 2x plus 1. Again, changing our signs. Okay, we've got nothing there, and then this gives us a minus 6. So realistically, our answer is going to be x plus 1 plus a negative 6 over 2x plus 1. But again, ignore the remainder, so really all the stuff that I just wrote is kind of meaningless. And what that means for us, graphically at least, is that our slant asymptote is going to be, actually let's use an arrow for that, is going to be the equation y equals whatever this answer up here was, in this case, x plus 1. Alright, so, okay, just quick note, there's the homework assignment. Just for space concerns, I stuck it here instead of at the end to save people a sheet of paper later. So here's how this guy's going to play out as the whole deal graphically. Okay, so with this function that we've got here, that we had the exact same function in the last slide that I used to do that division. Okay, kind of do what we did previously. Okay, start looking for a vertical asymptote. And so of course a 2x minus 1 is going to give us an x equals a negative 1/2 as a vertical asymptote. So we can immediately transfer that over to the graph if we want, or of course we can save that and kind of put everything on the graph all at once, just depends on your personal opinion. Okay, domain, of course, works out to be all reals except whatever that vertical asymptote was for us. So in this case, the negative 1/2. Okay, horizontal asymptotes. Well, if you remember the rules from the previous lesson, anytime the degree on top is higher, you're not going to have one. So, got no horizontal asymptote. And the slant asymptote, well, we just figured that out from the previous slide. That was y equals x plus 1. Again, technically with that negative 6 stuff over here, but again, we're going to ignore him. Alright. And then from there the zeros, and the zeros, okay, we just have to graph the numerator, factor the numerator, and we can factor that guy into a 2x and an x, and then we got to play around with a 5 and make a 3. We can do that by putting a 5 here and then 1 there, and then again to make all the signs work out right, we need a plus 5 and a minus 1. Of course, thinking that guy equal to 0, because we're trying to find zeros, gives us zeros, or x-intercepts, and negative 5/2, and is positive 1. Okay, before I start putting too much stuff on the graph, I do want to point out something again about the horizontal asymptotes and the slant. Now remember, the horizontal asymptotes we get if the degrees of the numerator and denominator are either equal or the denominator is greater. The slant only occurs when the degree of the numerator is exactly 1 higher. Okay, so here it's either a tie or the bottom is bigger. Here the top has to be bigger. So basically, you're never going to have both of those guys at the same time. So it's kind of nice, you only have to watch out for one or the other. As soon as you find one, you know you don't have the other. But anyway, here we go. Okay, so vertical asymptotes on the graph. Let's go down here to the slant asymptote. That's the next thing I actually have. Okay, and I've got my plus 1, and so I'll just kind of put down a few points to help guide myself here. Whoops, one right there, there. Ignore that other random blue dot. It's not really there. And these definitely are not the droids you're looking for. Alright, so we've got that. Okay, got a couple of zeros I can put on the graph, and negative 5/2. Now be careful, it's getting a little busy here, so just be careful you don't miscount. So negative 1, negative 2 1/2. and then the positive 1, well, that was a little easier to deal with. Okay, now at this point, again, I'm going to have to look for some other points in the regions between the zeros and the vertical asymptotes. Don't worry about the slant asymptote is coming up with other regions of the graph. The other ones will be good enough for us. Alright, so I need to go left of negative 2.5, so I'll just go with negative 4. Of course, I could have gone with negative 3, negative 4, negative 5, etc. I'll just use that. Okay, now I need to go to the right of negative 2.5, and negative 1 sounds good to me. Okay, after I get to the right of this negative 1/2, the asymptote, I'm going to use 0. Okay, whenever I have a chance, I'll definitely use that. And then I need to pick something to the right of 1, and I can pick 2, 3, 4, 5, 6, whatever. I'll go with 3. And I'm sure you guys don't want to watch me plug these values into this fraction and work them out by hand, so I'll just kind of tell you what I got. As I plug in the negative 4, I get actually negative 15/7. Okay, and that's technically negative 2 1/7, so basically just a little more than 2 as far as the graph goes. Negative 1 actually came out to be a nice clean positive 6. 0, hopefully by no shock, comes out to be negative 5. Okay, 0 is one you could always plug into the original, especially just lose everything that's got next in it and deal with what's left. And then as I plug in the 3, this is a little bit messier, but it works out to be 22/7. And kind of paying attention to that, it's actually just a little bit more than 3. Okay, so now plotting what we have, negative 4, negative slightly more than 2. So 1, 2, 3, 4, 1, 2, and down 1. Okay, now notice that's really, really close to this asymptote, and that's going to be kind of a common theme with these slant ones. A lot of times you're going to have points very close, so it's going to be very important to graph these guys accurately. So I'm sure you can tell by being a little bit sloppy, you might not be sure whether this dot's supposed to go above it or below it, and that will have a big impact on what the graph is going to look like, so be careful there. Okay, anyway, the negative 1 and positive 6. 1, 2, 3, 4, 5, 6 gives me a dot about right there. Okay, 0, negative 5. 1, 2, 3, 4, 5. And then finally 3, and then again just slightly more than 3. So 1, 2, 3, 1, 2, 3, and again just slightly more. Notice we're very, very close to that asymptote again. Okay, now drawing a nice smooth curve through what I have. Again, I want to hug this asymptote as best I can until I pass through this dot, and then again as I approach the vertical asymptote, and kind of assisted by this dot here, I should head off vertically. Okay, again, the big hint that I'm not going to have this guy turn around and go back down or something crazy like that is the fact that there's no 0 over here. Okay, there is one over here, but it's on the other side in the asymptote, and we always kind of smash up against the asymptote. Okay, as I get to the right of the negative 1/2 asymptote, I'm down here, so of course, again, since there's no 0 over here, to the left of 0, I have to be going down, hugging the asymptote there. And then of course I'll pass up through this other point, the 0, and then I'll approach the asymptote and pass through that point, and again hug this guy. And again, I know I'm not turning over and coming back down because there were no 0s over this way. So I now just continue that way and hug the asymptote. So there's how that graph plays out. Again, of course, if you'd like, type that in your calculator, and hopefully you should get something very much like that if you didn't mistype something. Of course, the asymptotes don't show up, so again, that is something you're going to have to understand on your own and be able to duplicate by yourself by hand. Alright, now with slant asymptotes in the books, another weird thing that can kind of happen that we haven't dealt with yet is something called a hole in the graph. Well, it's not an official name for it, but that's what I'm going to call it. Okay, now if a rational function's numerator and denominator have a common factor, there's going to be a hole in the graph. And as it says here, the hole is a single undefined value that won't be visible on your calculator. And so we have to know to look for it. And the way to do that is to factor the numerator and denominator and look for common factors. Okay, so this function here, the x squared plus 4x minus 12, or 2x minus 4, okay, if we factor that guy, it'll factor into an x minus 2, x plus 6 on top, and in the denominator I've got a 2 common factor, and I get an x minus 2 there. Okay, now in most scenarios, and what I'm going to do here, okay, if you see that, well, you cancel them out, and you say, okay, what do I have left? I have the x plus 6 over 2. Although, since we're dealing with a graphing scenario, this big fraction is a little bit sloppy to deal with, so I'm going to turn that into 1/2 x plus 3, because from a graphing standpoint, that's a heck of a lot nicer to look at. So basically, the graph of this nasty looking function will look exactly like the graph of the 1/2 x plus 3, but it's going to have a hole at x equals, well, whatever x value we lost here, and that's basically an x value of 2, because if you have x minus 2 equals 0, of course you get x equals 2 as an answer. Okay, so instead of a vertical asymptote, we're going to have that. So just as a really, really quick sketch, and feel free to check me on a calculator if you like, if I've got 1/2 x plus 3, I'm going to have, intercept of 3, let's just estimate, slope of 1/2, so it's going to be kind of flat-ish. But at 2, I'm going to actually have a hole. So the line would go something like this, and then an x value of 2, okay, going to have a hole. What we're going to do is represent that by a little open circle. Kind of like when you're graphing stuff on a number line and you don't want to include a value, you put an open circle there. Or at least you did before getting to this class and using interval notation. But again, that's beside the point. Okay, so basically that's what the graph will look like. Feel free to check that in a calculator, of course, and your calculator will look like a solid line. And no matter how much you zoom in, it'll never show you that because a single point has a effective width of 0. So again, it is something you have to look for. If you pull up the table for this function and you look at the x equals 2, it will give you an error message there. So that is one way to verify it with the calculator. But let's move along. Alright, here's another rational function, and then for this one I'll do the whole ball of wax. Alright, we got our f of x is x to the third plus 8 over 2x plus 4. Okay, hopefully right off the bat you go, oh yeah, that's one of those sum cubes things. So basically what we can do is we can factor our original function into x plus 2, and then x squared minus 2x plus 4. Okay, and then of course the denominator is a pretty easy factoring of x plus 2 with the 2 common factor, so the x plus 2's go away. So again, we've now identified that we do have a hole at x equals, again, whatever that x value would be, in this case, negative 2. Alright, now notice that's not going to be a vertical asymptote. And if you'd like, we can simplify this a little bit, make it a little nicer to deal with. And so what we've got is f of x kind of in quotes, because we've kind of messed with it now. Again, a 2 on the bottom is going to act as a 1/2 that I'm going to kind of carry through the whole thing. So it's 1/2 x squared. Okay, the 2's are going to cancel, leaving me with a minus x, and then the 4 and the 2 reduce down to a 2. Okay, so what I've got actually here is, hey, that's a parabola. Alright, so that's kind of what I'm going to graph, except I'm going to have a hole at x equals 2. Well, again, this is what I'm graphing, this parabola. So vertical asymptotes, well, parabolas don't have vertical asymptotes. None. Okay. Now what we do have to pay attention to if we've ever talked about domain, if we've got negative 2 as a hole, it means we have a bad x value. Vertical asymptotes none, I mean we don't have any more bad x values, so our domain is all reals except at negative 2. Alright, then horizontal asymptotes, again, I'm looking at this thing, it's a parabola. Well, I don't have any horizontal asymptotes for a parabola. And again, slant asymptotes, even back to the original, if the numerator is 1 higher, I've got myself a slant asymptote, and that's not the case here. So my slant asymptote also is none. A lot of nuns here. Anybody else feeling religious? Okay, and then from there we've got zeros. And so what we can do here is try to set this thing equal to 0. I'll save you the effort right now. If we were to set this thing equal to 0 and try to solve it, we'd end up getting i's. So as far as zeros, we've also got none. Alright. Okay, now we've got the other point sort of thing. Now I admit, since we're dealing with a parabola, I think the other points is kind of pointless, but So, okay, all we need to do is graph this parabola and just kind of remember that, hey, negative 2, so I'll just put this little tiny x on my graph to remember something. At negative 2, I'm going to have a hole. So I'm going to graph my parabola, and wherever it passes negative 2 in my x value, I'll just put a little circle there, and then just kind of go on graphing as normal. Okay, so what I need to do to graph a parabola, of course, is to do my x equals negative b over 2a things. I'm just going to get rid of this. Alright, x equals negative b, so negative 1 over 2a, so 2 times a half. I know, call the National Guard, that's a fraction. But we've got positive 1 on top, and actually positive 1 on the bottom, so it's really a 1. And as I plug this in, 1/2 times 1 squared minus 1 plus 2. Okay, again, the 1 squared is 1, and times 1/2 is a half. So 1/2 minus 1 is negative 1/2, and then negative 1/2 plus 2 is 1/2. So either 1/2, 1.5, 3/2, whatever you like. Basically, for our parabola, the vertex works out to be 1, comma, and then again, whatever version of that you prefer. So I've got 1 and then 1.5, so I'm right there. Okay, and then that 135 stuff still applies. Alright, I've got 1/2 as my lead coefficient, and then 135. Okay, so I'm going to have a 1/2, 3/2, and 5/2. So I'm going to do this to the right first for a very good reason. I'm going to go over 1 up a half, get a point. I'm going to go over 1 up 3/2, so that's 1.5 more. And then over 1 up 2.5, so the half gets me to this grid line, and then 2 more sends me right there. And then again, I can keep going that basic pattern forever, but now I want to come back to the left. So over 1 up a half again, over 1 up 1.5, Again, notice these guys line up with each other. But as I go over one more to the left, notice I hit my bad value, my hole value, if you will. So then I go up here, and instead of making a nice, pretty solid dot, I'm going to make an open dot. Okay, just again indicating that that bad value from the original problem playing out as a hole in my graph. Okay, so as I draw my parabola here, I just do a nice, pretty one on the left side, or sorry, on the right, but on the left, I come over here and just kind of do my best to represent that hole as I draw the rest of my parabola. So there's how that'll play out. Alrighty, take a look at this guy. Okay, now notice I'm working some blank space because there's actually going to be a lot of preliminary work we're going to have to do before filling in all those blanks to graph this thing. Those of you that already printed the PDF, you can see that I've got this lower down the page, but anyway, let's get to work. Okay, first thing first, I want to identify if there's any holes, and since I've got a cubic on top and a quadratic on the bottom, I've got 3 factors up here, 2 factors up here. There's a fair chance that one of those guys might match and we might have a hole, so factoring is going to be very important. Alright, so here we go. I can factor my original f of x, and I don't know how good you are at factoring by grouping without showing how any work, but anyway, this would be x squared, and then this will be x minus 2. Got a minus 9 over here, and then notice pulling out the negative 9 sends me with an x minus 2 there. Alright, and then the x minus 2 can come out in front, and then of course I'll be left with an x squared minus 9, which nicely factors into x plus 3, x minus 3. Alright, from there I've got this guy here, and I'm going to factor this guy. This one's a little easier to do all in one step. Okay, really no choice to have a 1 and a 3, and to get a plus 2 in the middle with a negative 3 there, I have to use a plus 3 and then a minus 1. Of course, notice that that means that those x plus 3's can be canceled out. So basically what that gives us is our slightly modified f of x is going to be x minus 2 and x minus 3. Alright, in the denominator, all we've got is that x minus 1, parentheses optional. Alright, so what that lets us know is that our graph is going to look like this. We're going to have a hole, and I'll fill this in on the next slide, but we've got a hole at x equals, again, whatever the bad value is, in this case negative 3, and we've got that. Also from here, since this is a very nicely factored form already, I'll save myself a little bit of effort and go, oh, my zeros are going to be at positive 2 and positive 3. Alright, and so that's kind of something we're going to be able to work with. Okay, another thing that we have to do is find out now, because bad news, I've got a square in a third power, so I've got a numerator that's 1 higher, so I'm going to have a slant asymptote. So I'm going to have to do division to get to where that slant asymptote is. Now the problem is the division that we know how to do is all built on having these guys as full-blown polynomials and not these factors. So I actually have to re-multiply this thing out and get an x squared minus 5x plus 6. Okay, the good news though is since this is a single kind of term that doesn't have a coefficient or an exponent, I can use synthetic division now. So I can put that 1 in the box and then put the 1, negative 5, and the 6 here and do my nice pretty division. 1, bring this to a 1, this comes out to be a negative 4, and then admittedly we don't care, although that comes out to be a 2. So again, my slant asymptote is going to be y equals 1x minus 4, and then again, technically plus 2 over original x minus 1, but again, we don't care. So my slant asymptote is going to be y equals x minus 4. I got my zeros, I got the hole, and that's most of the other work we're going to have to do. So basically now I'm just going to transfer that down to the next slide, and we'll keep rolling along with that. Alright, so picking up where we left off, a few things transferred into the right blanks here. Alright, again, we figured out where the hole was, the slant asymptote, and the zeros, and we figured out that our kind of modified f of x looks a little more like this guy. Although that's not one of our obvious graphs, like the parabola from the previous example. So we are going to have to do some work to figure out what this guy looks like as far as transferring everything onto the grid properly. Alright, so other things we haven't done yet, vertical asymptote. Well, I've got the x minus 1 that kind of survived on the bottom, so that lets me know I have a vertical asymptote of x equals 1. Okay, our domain now, notice the hole is a bad x value, and the vertical asymptote is a bad x value. So for our domain, it's all reals except negative 3 and positive 1. So basically any hole or vertical asymptote plays out as a bad domain value. Okay, horizontal asymptote, well, if you remember from before, since our numerator's degree is higher, it means we have none, or if you're just paying attention and said, hey, wait, we have a slant, so I automatically know I don't have a horizontal, There we go. Okay, so now we can transfer all this stuff onto the graph. Okay, again, what I did previously, the hole at x equals -3, I can just kind of give myself this little tiny x right there as remind myself that, hey, I've got a hole there someplace. My vertical asymptote is x equals 1, so put myself down a nice vertical asymptote there. Again, domain I don't really have to sweat so much. Horizontal asymptote don't have. This length is y equals x minus 4. 1, 2, 3, 4. Alright, and again, up 1 over 1 kind of deal. And just to be as careful as possible, feel free to plot a bunch of points. Okay, you know how sloppy you are, and some of you probably need to plot a bunch of points, and some of you are probably good enough to draw it completely freehand with your eyes closed after somebody spun you around 3 or 4 times. Alright, so there's all that. We put our zeros on the graph. Zeros are at 2 and 3, so we got a couple of zeros very tightly packed close together. So we've got that, and now we have to again play the other points game. Alright, now I do have an asymptote here and nothing but empty space. One thing you can do though, you can plug in x as the whole value if you want, and then plug it back into the kind of modified version, and that'll actually give you an exact location of the hole, which is sometimes a pretty good trick to go by. So I'm going to do that, but let's just pretend that we didn't notice that for a second and go, oh, okay, well, left of that lets me pick a 0, so I'll pick a 0 as well. Okay, and then we do have kind of a dicey situation between 1 and a 2 here. Well, I can't help but pick a fraction, so I'll just pick my 1 1/2. Alright, okay, and then kind of same problem here between the 2 and the 3. I don't have much of an option, so I'll just pick 2 1/2. And then once I make it past the 3, I have to pick something that's, well, bigger than 3, so I'll just pick 5. Alright, and then again, just saving you the torture of watching me explain how to do these things. I'll just give you the answers. The -3 gives me a -15/2 when I plug it into here. Of course, if I plugged it into the original, I'd end up with a 0 on the bottom, and that wouldn't help us out at all. Okay, as I plug in the 0, of course, well, I get 6 over -1 because all the x's canceled, so that just gives me a -6. Plugging in the 1 1/2 gives me, strangely enough, a 1 1/2. Trust me, that won't happen all the time. Plugging in the 2 1/2 gives me a -1/6, and then plugging the 5, by weird coincidence, also gives me a 1 1/2. Okay, so now I'm plugging in those points. Okay, my -3, again, that's where my little x was. Now, -15/2 is basically -7.5. Well, not basically, but exactly. So 1, 2, 3, 4, 5, 6, 7.5. Okay, again, notice how a little bit of sloppiness will end up putting us on the wrong side of this thing. So again, very important to graph your asymptotes as accurately as possible. Okay, 0 gives me -6, so 1, 2, 3, 4, 5, 6. Alright, the 1 1/2 gave me 1 1/2, so 1 1/2, 1 1/2 puts me at a point kind of floating free in space right there. Okay, the 2 1/2 is a -1/6, so just barely below the x-axis. And then the 5 gives me a 1 1/2. 1, 2, 3, 4, 5, 1 again. Be careful around your asymptotes. There you go. Okay, so believe it or not, this is enough to graph this thing. Okay, so down here we're below the asymptote, hugging it, so we're coming this way, and then again we come through this guy, and then we're like, well, what the heck do we do? Well, remember, okay, this vertical asymptote is something I can't cross, so I have a choice of either heading vertically or well, vertically up or vertically down. And if I head up, that means I'd have to cross here and have a 0, which I don't have, so my only option, really, is to turn and head south, so to speak. Okay, and then going over here, this other cluster of dots I have, I think these play themselves out pretty well. Okay, over here, I'm going to be hugging my asymptote as I go vertically. Again, I know I don't turn around and go back down because there'd be another 0 over here someplace. Okay, as I go to the right now, I kind of just pass through the x-axis, hit this -1/6, then pass back through the x-axis, and then again pass to this point as I hug my asymptote, and there's our complete graph. And I messed up and I didn't put the hole in the right spot, so pardon me for fixing it now, but that should be an open circle right there. Bad math teacher. Somebody make sure you slap me on the wrist during class. No, don't really do that. Okay, but anyway, there's the completed graph, complete with the hole that I forgot, pardon me, and there you go. Okay, of course, if you have any questions, come see me in class, and I guess I'll see you there.